Hi, this is Ms. Fitzmaurice, and this video is an introduction to waves. So while this might seem like it is a departure from learning about energy, it turns out that waves are basically energy traveling through a distance. And so by the end of this video, you should have a definition of what a wave is, so the formal physics definition. We're going to go over some basic wave terms and some basic types of waves, and then I'm also going to introduce to you the wave speed equation, which you've probably seen in chemistry, but it'll just be a good reminder. Okay, so first of all, let's go over the formal definition of a wave. A wave is basically any time you have energy moving through a distance without the matter moving through. So energy, but importantly, not matter, moves through a distance. Okay, so, some obvious examples would be like ocean waves, sound waves, and what I'm going to point out to you for an ocean wave is that the water molecules right here, they might go up and down, okay, but let's say that the waves are coming in this way and say here's the beach. This water molecule right here, it will go up and down, and the wave travels in towards the beach, but this water molecule that I highlighted in red does not move in the direction of the wave. It just stays in that position and moves up and down. It doesn't travel side to side. Okay, so the three types of waves we're going to talk about, actually, let's say there are four types. There's transverse waves, there are longitudinal waves, and then we're going to talk about electromagnetic waves, and also mechanical waves. Okay, so transverse waves, and I'm going to give an example of if you had a slinky and you had waves moving through it, and let's say this is your slinky and the waves are moving in this direction. Basically, the definition of a transverse wave is that the direction the wave or the disturbance moves, so I'm going to say the wave moves, is perpendicular. I'm just going to draw the perpendicular symbol from math to the displacement in the wave. Okay, so as you can see, let's say there are two people standing on each end holding the slinky. Here's a person, and let's say the wave's traveling towards my second person. So that's the direction, this red arrow is the direction of the movement, but each slinky coil is moving up and down, and so the direction that it's moving is perpendicular. It's moving side to side. The wave is moving up and down. Those are perpendicular, so it is a transverse wave. In longitudinal waves, and again, I'm going to give you an example with a slinky first because I think that's the most basic way to illustrate it. So let's say that instead of moving your arm up and down, you push into the slinky, and you get this pattern where sometimes the slinky coils end up really close together and sometimes they end up farther apart. And let's say that the disturbance, like the coils that are close together, those are moving again along the slinky this direction. But now if we look at this individual coil, this coil, it doesn't travel down to the end, but it moves back and forth along the slinky. And you can remember longitudinal, it travels along in the same direction. And so the definition is that the direction the wave moves is parallel, and I'm just going to make the parallel signs from geometry, to the displacement. Okay, so the other two types of waves are electromagnetic waves and mechanical waves. Electromagnetic waves, and I'm going to give you examples first. So examples would be like light, X-rays, UV rays, infrared. Okay, and a lot of you guys will be writing about electromagnetic waves in your paper. They are waves in which there's a disturbance in electric I'm going to separate these, in magnetic fields, and we'll get into more detail about that later on. Mechanical waves are waves, and they have to travel through material. So waves that travel through material and the disturbance or the energy moving through the wave is displacement of actual molecules. Alright, so mechanical waves and electromagnetic waves differ in one other way, besides what material they're going through. So electromagnetic waves, they don't require material to travel. Mechanical waves, they all require material. But also, mechanical waves can be either transverse or longitudinal. So an example would be earthquake waves Okay, if there's an earthquake, the longitudinal waves would come from a place, and it would probably, if that place was near to your house, it would shake your house from side to side. So I'm going to put L for longitudinal. And again, if it was near your house and the waves were traveling towards your house, the transverse waves would shake your house up and down. Electromagnetic waves, on the other hand, can only be transverse. Okay, so basically an electromagnetic wave is a wave with electric and magnetic fields, and we'll talk a lot more about that later. Okay, but let's say that this red arrow is the direction that the wave is traveling, and my blue arrows right here are an electric field. The electric field will always be perpendicular to the direction the wave's moving, so and then the magnetic field will also be perpendicular to both of those. So your wave will look something like this. And I know this picture is a little bit hard to see. I'll show you a 3D version. But the important thing to remember for right now is that electromagnetic waves are always transverse. The last two terms I'm going to introduce you to today are wavelength and amplitude. So let's say that we have this slinky wave that I've drawn in. If we put it on a graph of xy, so the vertical position, this is our xy, versus xx, and that's our horizontal position, xx, it will look kind of like a snapshot of the wave. It'll look like this graph right here. Now, the wavelength is the distance between two repetitions of a wave. So this is our wavelength, and we'll measure that in meters. And the symbol for wavelength is this Greek letter called lambda. And it looks kind of like a T where the top is sideways. Okay, the other term is amplitude. So the amplitude is half of the height of a wave. Okay, and then finally I'm going to introduce you to two ways to measure the speed of a wave. The first way is just like we're used to. So you could measure how long it took a wave to get to the other side of something. So this would be distance, of course, in meters, divided by time. But the other thing that we can do to calculate wave speed is by multiplying our wavelength times the frequency. Okay, and remember, frequency is in hertz and wavelength is in meters.